Hi, everybody. Welcome to Chapter 17, which is Sound. This is actually our last chapter, our last module for the course, and it has been a wild and crazy semester and not what any of us expected, but congratulations for persevering. Congratulations for continuing to work under circumstances that nobody could have predicted. I hope you enjoy this chapter. It is not terribly complicated. The math is no more difficult than anything you have encountered, and in many ways, it is easier. A lot of students get to this point, and I totally understand if you are a little bit tired and a little bit worn out. Emotionally, it's been quite a semester, and I know you've got a lot of other things going on in your life as well as schoolwork. So it's a good place to finish is with sound and waves. They're fun, they're interesting. You're going to find that there's a lot more vocabulary. There's a lot more ideas with sound and waves. Of course, there are going to be a few more equations, none of which are more difficult or more complicated than anything else we've had so far. But you are very capable of doing the math at this point in time. Those of you who are in the DMS program or pre-DMS, I totally understand that many of you are. Please pay close attention because the ideas from this chapter are vital. You are going to see these all again in ultrasound physics. And this is, everything has been leading up until this point. Waves are how energy gets transferred. Waves are how work gets done from place to place by light waves and sound waves. So they're really important in lots of places. So before we continue, or as we continue, let's go over to Canvas and take an overview. So we're going to do a little bit of an introduction to waves, how waves operate. As always, we'll have a study guide. And then we're going to have multiple lectures on vocabulary and ideas. Many, many, many lectures with lots of example YouTube videos tossed in. When I choose YouTube example videos, I try and choose things that are short, couple minutes or less, because I totally understand that if they're too long, you don't want to watch them. So please watch those because in class, I would be doing a lot of demonstrations for this chapter. And at a distance, I can't do that. So here's a lot of information. And you have to get down to the wave equations before you can start the homework problems. This is a big 2-week chapter. When you start the homework problems, notice there are many of them. There are 31 of them. So please start those as soon as you can. And as always, do not wait till the last minute. If not, you will be in deep toast. The Doppler effect, big important idea in everything from car horns to weather radar to astronomy to ultrasound, knowing if blood is flowing into or out of the heart. Standing waves in open and closed pipes and strings. Decibels, how the level of sound, the loudness of sound is related to that. Bow waves, also known as sonic booms, very interesting concept. We have one lab for all of this. Everything for the entire chapter is due the last moment of the semester. So everything is due except for the lab. The lab is due the Sunday before at midnight, but the homework, study guide, the tests, concept quiz, and problem test just over sound is due midnight, May 14th, which happens to be that last moment of the semester. And that is when it's all over, ladies and gents. So if you can do anything ahead of time, highly recommend it. Let's go forth and take a look at the lab. As always, we're going to start with the paper version of the lab, and then we are going to transition to what changes that have been made because you're doing this at home. The first part of the lab looks almost identical in the at-home lab versus what you have in your packet. I'm asking you to sketch out the resonant wavelengths on strings, open and closed pipes. Now, these are all discussed in the notes, so please consult the lecture videos to know how to do these. Look at the reminders for strings, the resonant wavelengths for the fundamental first, second, third, and fourth overtone. Remember, for strings, they go up in whole multiples of a half wavelength with a node at both ends. In here, please fill in what fraction of wavelengths each one of these represents. Closed pipes, these, again, sketch in here the shape that is going to be produced, write down which overtone there is, and in here write down the wavelengths, the fraction of wavelengths. These go up as odd overtones, odd intervals of quarter wavelength with a node at the closed end and an antinode at the open end. Right now that may sound like gibberish. After you've watched the lectures, it will make sense. Open pipes go up as multiples of 1/2 wavelength with an antinode at both ends. Again, in here, you're going to do that sketching, writing down the overtone and writing in the wavelength. So that sketching is important because you have to understand all of these in order to do the homework problems. And trust me, on the test, you are going to have string problems, opened and closed pipe problems. So that's important that you understand. This is the experimental part of the lab. I'm very sad we can't do this in person because this is a cool lab. This lab involves finding the velocity of sound using a tuning fork and using a ruler. So a tuning fork and a ruler or a meter stick to measure the speed of sound, pretty cool stuff. First thing you're going to do is calculate the true speed of sound using the air temperature. You can do that right on this page here. And then for the at-home packet lab, what I would do if we were doing this in class is I would have you use 2 different tuning forks. In the modified version, you're going to use 1 fork, just 1 fork, and you're going to use the first, second, and what you're actually going to be doing is you're going to be doing the 3rd resonance length, and you are not going to be doing this one. So you can chop this last column off, and you are going to be doing the first 3 columns, and that's what you're going to be using. Please consult the at-home version of the lab if you don't have access to a printer, because I give a lot more detail in the data chart on the at-home version of the lab. The part 3, if you're using the paper and pencil version of the lab, all of this can be crossed out. You don't have to do it. We're cutting that because you do not have tuning forks at your disposal. But one of the things that I am asking everyone to do is this calculation. So yes, you are going to be doing this, and that is my mom always taught me that when you see lightning, you start counting, and for every second until you hear thunder, that was a mile. Well, my mother was an English major and her math was wrong. So what I'm going to ask everyone to do is to calculate how much time it takes for lightning to travel a mile, how much time it takes for sound waves or thunder to travel a mile, and then round that off to a number of seconds, because my goal is to make you the smart parent so that you can teach your child the right way. So this is the modified at-home version of this lab, and it looks very, very similar. So we're going to start with drawing those wave shapes. So this looks identical pretty much to what you have in your packet. A lot more detail of exactly how the lab was conducted, complete with some data. So please use the air temperature, because I did this lab on my kitchen table. Current air temperature, 18 degrees Celsius on the day I did it. I'm going to ask you to calculate the true value using an equation you're going to find in your notes for the corrected speed of sound, corrected for temperature. So that equation is actually in your notes. How the lab is conducted is a clear plastic tube is put into a graduated cylinder. This is raised up and down, and it produces a closed pipe. The bottom end is closed, the upper end is open, and by raising and lowering the pipe, you create different resonant lengths. Holding the tuning fork above this, you can determine or find the spot by listening. You can actually hear the places where antinodes or amplitudes, high amplitudes of sound are created. I made myself a little video of me doing this lab right there. It's a little 40-second video. I highly recommend that you watch it. And I also found another really quick minute or so video of other people doing this with different tuning forks. So I'd like to have you watch both of those so you get an idea of how this lab actually works. Because you cannot take the data well using the videotape, here are the resonant lengths I'm going to ask you to use. 4 centimeters, 12 centimeters, and 21 centimeters. Plug those numbers and back into here. You're going to need the frequency of the fork. The frequency of the tuning fork used is, I have that somewhere. I better have that somewhere. Where is the frequency of the fork? There we go, 2048 hertz. You're going to plug that information into the data table. The resonance length is what is given earlier in the lab. The frequency is given earlier in the lab. And then what fraction of the wavelength does the resonance equal? Where do you get that? You get that from right here in that chart. Okay, that's where you get that information. Algebraically rearrange this equation to solve for wavelength. So all you do in this column, this row, is algebra. Solve this for wavelength. Solve this for wavelength. Solve this for wavelength. Number 5, use the numbers from row 4. Use the wavelength equation from row 4, put in the numbers from row 2, find me wavelength. And you're going to do that here, here, and here. And then lastly, in row 6, you're going to calculate the velocity of sound found during this experiment. So you're going to use the wavelength found here. You are going to use the frequency found here, put those into this equation, and that's going to give you your experimental value for the wavelength of sound, velocity of sound on this day. Then you're going to calculate a percent error. Where are you going to find that true value? Well, the true value was, the true value is right here. You calculated that earlier when you corrected the speed of sound for air temperature on this day. Then, as always, show me a percent error. Now, I am not asking you to show me all your work. This is our last lab together. I'm going to make the crazy assumption you know what you're doing. And I hope you do at this point in time. So just fill this in carefully. Make sure you've got correct units on everything. Make sure you convert from centimeters to meters. And keep this in mind. This is one tuning fork. The same tuning fork was used for all measurements. Because it's the same tuning fork and the same frequency, all of these wavelengths should be the same. So if you get one of these that's way wacky and different than the others, odds are you made a mathematical error. So that should be a big hint. If all of these are pretty close, you did the math right. If all of these are pretty close, you did the math right. Last but not least, same thing I'm asking you on the paper and pencil lab, do the lightning and thunder comparison. And that is going to be all she wrote. So thank you. For some of you, this is going to be the last video and last time I get to talk to you. It's been fun. I am saddened by the fact that I do not get a chance to sit down with you. And many of you I got to know quite well. Some of you were quieter and I didn't get a chance to know you as well. But thank you for persevering. Thank you for putting up with a weird and wacky situation. And you can be very, very proud of yourself. It is a sense of strongness, a sense of accomplishment. It is easy to quit when the going gets tough. And it is a mark of strength of character to keep going when things turn left on you. So I am very proud of each and every one of you. Some of you it's harder for some of you than others. And for all of you, I am just incredibly proud to work with you. So best of luck when we do encounter each other in the hallway or when we can actually be in a Menards together. If you see me, please throw something at me and say, hi, Mary. And hopefully I'll talk to you soon. All right. Bye-bye.